Wait, so we've gotten 4 solutions for 2 questions in the last half hour.
Nice, nice. Okay, I think this back up.
Yay.
That was tragic. All right. Where is it? Okay. Let's see.
Oh.
All right, okay. Stream looks good.
Is my audio working?
Yep, it is. But it's a new stream. That's
Okay.
very sad. Sharky, we get it. You're popular.
Huh? And what? What happened?
We heard your messenger notification.
Oh, right.
All right, should we start problem 3?
Yep.
I mean problem 7.
Let's start.
Yeah.
Each of the n squared cells within my ingredient is colored. Wait, what is this? This was first one was like combi number theory.
Yeah.
Second, geo. Third one's just combi, and fourth one's out. What is this combi?
Wait, yeah, sorry. I'm back.
Yep.
Yeah, no. I heard there were comments saying like day 2 was like just combi stuff.
Okay.
Anyway, I'm just reading the question now.
Yeah.
Oh, interesting.
So n equals 1, 0, right?
Yeah.
Let's just draw all possible 2 colorings of 2 by 2.
Sure.
This is gonna be what? So AI is number of light cells in the iPhone. So 1 times 1 plus 2 times 0.
Surely
So
this
1.
is some sort of like. I feel like this is some sort of rearrangement inequality thing where you have the optimal solution is like you have the diagonal, and then everything above the diagonal is like white, and then everything below is like black.
Maybe. Yeah, that's what I was thinking. Something like that. But I just want to double check that it actually works, right?
Yeah.
So this will be white rows, black columns. Okay, so 1 by 2 plus 1 by 2, that's 4. This is going to be okay. So for example, I think 4 is the biggest you can get for n equals 2, right?
Okay. Yeah.
It looks like the biggest because it's like 1 by 2 plus 1 by 2.
Wait, what about
And
what about
1?
this
By one.
configuration, but you like rotate it.
Rotate in which direction? It'd be the same.
90 degrees anti-clockwise? Is it just the same?
Would it not be the same? 2 by. Oh wait, what?
Yeah, it's different, right? Yeah.
Oh god, yeah. I could just skip some stuff as, you know.
So this one is 4 as well, right?
Is it?
2 by 1 and 2 by 1, right?
Yeah. Interesting.
So, like, obviously, if you flip it along this diagonal, it's the same.
Yeah.
Yeah, because the whole thing is like the squares on the diagonal are like not symmetric, but the squares off the diagonal are symmetric, right?
Yeah. Right.
So okay, let's have a look here. If this was like the best coloring available, this would be like n squared n minus 1. Oh wait, no, hang on. Sharky, this isn't 4, this is 0. Oh no, sorry, this is 2, right? Because the number of blacks in the second
Oh yeah, yeah.
column is 0.
Yeah.
And likewise, this should also not be 4 because you get 1 times 2, and then you just get 0 times 1. So this should be 2 as well.
Okay. Not bad. Okay, so 2 is probably the maximum. Okay, well, I like your idea of having this kind of black-white thing. So let's try this construction then, where it's like you have the diagonals white, so your major diagonal is white, and then everything below is black.
Yeah, exactly, and everything above is white, right?
Yeah.
So you'd get n, sorry, not squared, n times n minus 1. And don't you just sum that from like 1 to n?
Yeah.
So hang on, it would be like sum I equals 1 to n of I n minus 1. I think it's from 0 to n actually, but 0 obviously doesn't work. Oops, sorry, it's an I.
Yep. This should get you what? Let's think. So n minus 1 plus n minus 1.
Oh, this is the sum of. Hang on.
And this is what?
6.
1 times 0. Yes. This formula.
Yeah, it's that formula. Yeah. It's the. Oh, it's the, like 2 times Pascal's triangle. Like.
It's like n minus 1 n plus 1, right?
Is it? What is it? Oh,
Yeah,
you're over here already.
And it's because
the first one you get 0, and then you 2, and then you have 6, and then you have 12, and then 20, and so on. So the sums are just 2, 8, 20, 40. Which is...
This is some triangle numbers.
Yeah, it is, which is like the next row, the next diagonal in Pascal's triangle, right?
Exactly.
So
it's n choose 3 divided by 2. Times 2, sorry.
Times
because
2.
It's
Yeah.
Not half. Yeah.
N choose
That's what I
2
did.
times 2. So this is our conjecture.
Yeah.
Wait, n choose 3? What about 2 then? Are you sure it's not n choose 2?
You don't choose 3, right?
Wait, but then what about 2? Don't you get 0 for 2 as well?
Um, hmm,
Wait, hang on, what? Or is it n plus 1 choose 3? It could be that.
hey, 10 plus 1 choose 3, my bad.
Yeah. That looks better.
Yeah. See, I had the formula right up there.
Yeah.
I was like, okay, there. Now, how would you prove this is optimum? Yes, probably rearrangement, right?
That's what I feel like, but it's not exactly rearrangement.
Can we prove that like if like there's a black in like this upper diagonal, then if you replace that black square with a white square, it doesn't decrease the score.
Oh, okay, maybe.
Although
Although it would decrease the score if we flipped black and white for the configuration, then it
all
would
right,
decrease the score, right? Yeah.
yeah. Wait, would it?
Well,
If you
because
switch black and white, then your score would be different, right?
no, as in like we like swap black and white in the configuration that we have, right?
Yeah, in the
So then,
configuration we have, if you switch black and white,
then we have,
then
then you're saying that if we change one of the blacks on the in the top right to a white, then we don't decrease the score. But I don't think that's true, because that means you can just change like everything to black, right?
wait, I'm not too sure because like you have a black up here somewhere, then it's gonna be in the sum as like a column, and then in the row it's gonna reduce the white. I think you can arrange, you can reorder the rows.
Oh, hang on, sorry. I need to reconfigure my. Yeah, okay, keep going. Sorry.
Wait, so you rearrange the columns, right, in whatever order, and you want to change the score. Yeah. Wait, no, wait, it will change the score, won't it? Wait, let me think. Would it? Surely not.
Reconfigure the.
You can order the row, order the column, sorry, right? You can or put them in any order for arbitrary configuration.
Um. Can you? Isn't that exactly what is not allowed by rearrangement theorem?
Wait. Okay, but if you order in so that the blacks are like in decreasing, then that should be like your maximum then, right?
Okay,
By
yeah.
rearrangement.
I just realized. So what rearrangement proves is that um, you have like for every configuration, um, like if the white squares don't adhere to like this gravity thing, then it's not the optimal. So you can like swap the rows and columns and
Yeah.
get a better one.
Get a better one.
So basically, if we treat each column as having like some number of blacks, then that number has to decrease as we go from left to right.
Yeah. Well, not be increasing. You can have it.
Yeah. But does that affect? Okay, but sometimes you can't necessarily have that be true while also having the whites be true as well. This is similar to um, ICMC problem 3 in round 1 or something. I don't know if you saw the paper, but like
I did yesterday.
basically whenever you have like a white, black, black, white configuration, doesn't matter which two rows and which columns, right? As long as they're like
Mm-hmm.
in a rectangle form, then you can never like um, you can't get rid of that configuration, which means that you can't just have like all the blacks be on the bottom left and all the whites be on the top right kind of thing.
Yeah, makes sense.
So I think maybe we can just show that we can get rid of all of the balanced tables to
Mm.
because that's what this configuration was called in that ICMC problem.
Rec- what was it? Rectangle free or something?
So
Um,
like each of these like four vertices that made a rectangle was called a table, and if you had like white black, and
yeah,
it
yeah,
was called balanced. Yeah,
yeah. I saw the paper yesterday. I still can't remember the exact question.
right. Okay, here's an interesting observation. So, swapping like rearranging the order of each column. I mean, sorry, rearranging the order of the columns doesn't change how many white squares are in each row. So we can do that to get like the optimal placement of black squares. And then we can repeat that for the rows. So we get like optimal arrangement of white squares. Right? And then that will just give us like the optimum value we can get for that equivalence class of colorings. So okay, so basically for any coloring, we call all the permutations of that coloring, as in like swapping the rows and swapping the columns. That's like the equivalence class of that coloring, right? So from each equivalence class, we only need to consider the coloring so that the white squares in the rows, they're like the most white squares on the top row, and then the second most white squares on the second row.
Yeah.
Yeah, and then we can consider the same for blacks as well. So the most black squares in the left column, and then second most black squares in the second to left column, and so on. And both of those conditions can be simultaneously satisfied. So like for each equivalence class, there is one element of that class, so that both of these
Okay.
are simultaneously satisfied.
Yeah. Okay. Hmm. I'm just gonna think about this a bit more though.
Oh, and by the way, sorry to interrupt again, but like for problem 2, I realized that my argument, like we weren't, my argument for the last thing wasn't actually finished. Um, but basically, like My argument was that if all the lengths are the same, then they have the same height. And if you change the length of any actual length, then like the height of that side changes. So like that means the heights become unequal, right? But that doesn't
Yeah.
work if one of the side lengths is like horizontal. But if one of the side lengths is horizontal, then on the other side, it must also be horizontal. And that means that you actually have like a degenerate n gon. So it becomes like an n minus one gon. And that's also why it doesn't work for the even case. And it only works
Your
for the
audio
odd
stopped
case.
working good. I just missed a little bit of like the last
Oh, can you hear me
30
now?
seconds. Yes, I can hear you now, but like 30 seconds ago, I was like, you just went silent.
Oh, okay, okay, sorry. So what I was saying is that for problem two, my solution wasn't complete in the sense that um, if you go, if like one of the lengths becomes horizontal, then like no matter how much you increase or decrease that length, the height of that side is not going to change, right? But if one of the lengths is horizontal, then the same length on the other side has to be horizontal, which means that you actually get like a degenerate n gon. So it becomes an n minus one gon.
Right.
Yeah, so that can't work either, obviously.
Okay.
I was going to say that before when I thought about it, but then I forgot because my computer died. So.
Okay, I have an idea. So now we have like ordering, right?
Yeah.
So you consider this square and like this row, this column below it, and this like row next to it.
Yep.
Now, if you have a white square, if you replace with a black square, then by rearrangement, I think that increases the value, the score of the board.
If you replace what with a black square?
If you replaced a white that was along this row with a black, then it should increase the score of the board,
Really?
shouldn't it?
So you mean like we change one of these to a black?
If there's a white in here and you replace it with the black, so like it becomes like A1. No, along this column. Sorry, you can't see where I've been highlighting because the way I've been putting my cursor up and down because you can't see a cursor.
Yeah, exactly. I can't. Yeah. You have to
Okay,
draw it
so
in.
along this, if you replace a white square with a black square,
Yeah.
then your score should increase, or at the very least, not decrease. I think.
Oh, oh. Oh, I see what you mean.
So like if A1 has like this is S equals to S plus A1 minus BI. So you're gonna show A this number of whites in here minus number of blacks in like the I column is gonna be greater than zero, greater than equal to zero. And it should be like for I greater than 2, I think. Oh yeah, yeah. So this works if we make it if we can reorder, we can order such that A1 is like your biggest value, the one with the most value out of A1 A2 through to AN and B1 B2 through to BN, right?
Yeah.
We can reorder. So therefore, this is greater this is greater than equal to greater than equal to S. So therefore, we can do that.
We can
So we
do
can
it.
assume all these ones in here are black. We can assume this.
Right. Okay.
Does that make sense?
Let me think about that.
A1 equals to like max. What is it? A1, B1, A2, B2, AN, BN. Because we can set this to be true. S is like your score of the old board, and then like if you switch the I square here, which is white, to black, then this is your net change, A1 minus BI. And that's going to S.
AI. Right. Oh, yes, yes. Okay,
Yeah.
okay.
And now, if we switch black in here to a
Right.
white, we
So I
can do a
think what we
similar.
just proved is that there are no balanced tables.
Yeah.
Right? Yeah. Okay.
And if we like do the same thing on the top row, right? I
Yeah.
think that
Then
will
everything
work.
is white. Yeah, yeah, yeah. I get that.
And then therefore we can just induct downwards. Yeah,
Right.
because that
Yeah, yeah.
this bit's done. We just have an M minus one by M minus one board, and we know the optimum for that by induction or something.
So what happens if like what happens is this is black?
Um. Hmm. Does it actually change the score?
Well, not if the rest of the board is like symmetric with respect to white and black.
Yeah. It shouldn't change the score, right? Because this will just be M minus one N, and that'll be the only time this score is counted. And it'll always be M minus one N by our argument.
Okay.
Yeah, so it's fine. Okay. That one can be either.
Right. So like all the squares along the diagonal can be either, right? Oh yeah, yeah, yeah.
Yeah.
That works.
If you have the symmetry thing, yeah. So yeah, so therefore we can get M minus one N for this L, and then you just induct downwards. Alright, that works, I think. And that's optimality. Well, we just double check the white thing.
Yeah, yeah. I want to double check the solution because we like kind of vaguely went through a lot of different things.
Okay, so from this thing, we know that now that if we can do this, that means B1's like greater than N minus 1 now. Yeah, it's either N minus 1 or N. So if we replace one in the top row from white to black, black to white, it's like what, A1
Wait,
minus
why do we know
1?
it's greater than or equal to n minus one?
Because we've just, this
Oh,
thing
oh,
shows,
oh, 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 because you can like change the whites to black, right? And yeah,
yeah,
yeah, yeah, and yeah.
A1 minus 1, B1 plus dot 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 plus, what is this, AI, BI minus 1 plus dot dot dot, and this equals to S. Oh wait, this should be a. Wait, which ones have I added? Yeah, this should be a plus here, right? No wait, you replaced a black with a white, so therefore this one. Sorry, yeah, S plus B1 minus AI, and that's going to go to 0 again because like if AI is N, then like wait, what happens if AI is N? AI. Oh yeah, because this is one of these is at least black, right? AI is at most M minus. So sorry, this is S. Yeah, this works. Yeah, that works. Do you see it?
Hang on, I'm still thinking about it.
What are you thinking about?
I'm trying to convince myself, but otherwise, it should be all good. I'm just trying to work out the details, basically.
I haven't I done the details, or is this about the rearranging part?
Um, yeah, like I'm trying to do the whole thing, like so part of it is the rearranging part as well. So right now, like wait, so if you change this, then this increases by I guess this, and make it to here. Right. Yep.
Okay.
Um. So basically, our argument is that um, so first you rearrange the grid so that's like it goes the rows of blacks go from like greatest to smallest, and then like the
No,
columns.
my thing doesn't use that.
Oh really?
Yeah.
Oh, okay.
Mine just needs your top row to be white, or like the biggest, most white row.
The most white row.
As in it's the most it's the row which has the maximum value.
Oh, the maximum number of whites.
And blacks. It should have like A1's the maximum of A1 and B1, A2 and B2, all the way to AN and BN.
Okay.
And I think we can do that, right?
Wait. A A1 is the maximum of what?
A1 through to AN and B1 through to
Oh,
BN.
all right. You wrote it here. Yeah, I see it.
Yeah. That's how like the first thing works. Otherwise, I can't even claim A1 minus BI greater than equal to 0. And we can do this because we have like um, ordering. And we can just log this. I think we don't even have to be able to reorder, right? Because once
Probably.
it works, yeah, because you can just pull it out and stuff. Yeah, so this works, right? Let me double check. If instead it was like A2, that was the maximum. Then we look at A2. It's like you look at A2 and you look at B2. Yeah. So basically, look at A. If A if AI is the biggest, then you can look at AI and BI as your row column, and you can show that it's like best to like have the thing have the column all black and the row all white, and the center itself could be any color, and then we can just pull that out and you just reduce to an n-1 by n-1 board. Yeah, it works. You need
Okay.
reorder. Nice.
I mean, wait. But for the reduction argument, that you're saying like it reduces to an n minus one by n minus one, right?
Yeah.
Um, then is your argument that like we don't have to worry about like these squares? Because if you reduce to the n minus one by n minus one, right, and it's like this, then you're
Well,
like you're getting rid of
every
these
square
two.
loses one. No, but the thing is, every square just loses one value, right? Every row and column loses one value, so it shouldn't actually change the.
Oh right, yeah, yeah. So you're getting rid of all of these, like for
Yeah,
yeah, in the context of like yeah.
yeah. By reducing, you're just so getting rid of like you're reducing each row's value and each column's value by one. Because of our argument, we can say that
Wait, but can we actually reduce?
if a like if okay if some like if some a b is maximal, then some a minus one b minus one is also maximal. Like where a and b like some permutations or whatever. Then this is also maximal for like the a numbers a minus one b minus one etc.
Okay.
Yeah, that just follows from rearrangement inequality. You've basically translated the entire sum, right? Does that make
Okay.
sense?
I mean, yeah. Okay. I.
Because you've translated everything, so your order doesn't actually change.
Yes.
So therefore, your sum would change value, of course, but like
Yeah.
the maximum will still occur at the same permutation.
Okay. Okay. I mean, yeah, yeah. That sounds about right.
Wait, if this is all wait, let me think something. Yeah, so if you wait, do you need this? Because I just realized I was thinking of it the wrong way. Because this is all white, right? If it was say like if this was say the maximum,
Yeah.
like A3, and this is all black, yeah,
Yeah.
then like if you remove this, then this column doesn't change value. These columns don't change value.
Wait, what? Which columns don't change?
The columns are just highlighted.
Oh.
Those don't change value, and these rows don't change value. So you don't actually need this at all, because the values don't change at all.
Oh. Oh. Oh, I see what you mean.
Yeah.
But then that means like we need to prove that there is like a row with like everything is white.
Well, this could be anything, remember, and we've
Sorry.
proven that already. This is what this is all about, right?
Oh, is it? Oh, okay. I didn't
Yeah,
realize.
that's what this is proving. This is proving that this is maximized when your blacks are all in one column and your whites are all in a row.
Oh, okay.
Yeah,
Interesting.
and you didn't even reorder. That's very cool.
Okay. I mean, you know, I'm pretty sure. I'm. Yeah. That's yeah.
That didn't take us too long, like half an hour ish.
Something like that.
Something like that. Okay, problem 8. This looks. Will problem 8 be like problem 4 last week?
Apparently not. I mean, people actually solved this one, so
Huh?
people actually solved this one.
So should be all right then. What is the sequence? So AM of the first n terms is greater than QM of the next of the n plus 1 terms, first n plus 1 terms. Okay.
Oh no, it's algebra. That's bad. Or bad
So
for
you
me.
okay. What should I do? I feel like expanding is the right thing to do. Don't you?
I haven't read the problem yet.
Oh, it's an inequality, so I'm just going to assume that expanding works. Actually, no, let's think about this. Let's try some small.
What? Okay. This is
A1
interesting.
equals 1. So 1 greater than equal to square root of A1 squared plus A2 squared plus 1. A2 is less than equal to 1. Because it's positive. Okay, I think it's because it's infinite, but that's why it has to be constant, right? Otherwise, you'll get something that's like
Yeah, obviously, yeah.
negative.
Yeah.
From,
I'm pretty sure
well,
if
I
it's
think why
finite,
can't
then
it
you can just
be
construct
converging
some
to zero?
weird.
Why can't it be a sequence converging to 0 though? Like if I said like A2 to be like a half, let's see what happens. Maybe just like straight up becomes like impossible eventually. So 3 and 4 less than equal to square root of
Greater
A3.
than or equal to.
Wait, no. I can't even. This would be 5 on 4. Wait. Yeah, it would be
Wait, why is it not
27.
that? It would be 27, right? Yeah.
And there'd be 7 on 16. Square root 7 on 4. Well, you can
Wait,
get rid of the square. Well, you can get rid of all this.
wait, what? What are we doing?
I already updated it. Square root 7 on 4.
How's it square 7 before?
A3, let's think of that. You sub that in.
What?
You sub that in, it works, right?
I see.
I just kept figuring out the value. I kept updating it.
Okay, okay. Sure.
Sure. Hmm. Let's see what happens if A3 equals to a quarter. I'm just gonna keep halving it until I can.
Yeah, yeah. That seems like a good idea.
So it'll be what? Next one's gonna be 7 on 8. If I did that right. Wait, no. What's the half quarter? 7 on 4. So it'd be 7 on 16. No, it'd be 7 on 12. Equal to square root of A4 squared plus, what's this squared? So 5 on 4 plus 1, 16 is going to be 21 over 16. $49 over 144 times number 4, that's going to be 36. Minus 21 over 16. Oh, I told you just. No, 6, 4. And then minus 21 times 9, 189, so 7. Squared 7 on 12. What is this?
Really? That doesn't seem right.
Seem right. 7 over 144 plus 189 over 144 is going to be 196 over 144. And 196 is like going to be, 2 over 4 is 49, so it's 49 over 144, which is 7 over 12.
Okay.
What is this? Is 1 over 8 smaller than this? Should be, right?
Yes.
Even before this question's wrong. Now it'll probably fake solve it if that happened.
Yeah.
Yeah, I'm fairly sure that this gap's getting closing in. Because before I couldn't even tell now that this is bigger.
I mean, it's kind of, it's not that bad, but
Yeah,
yeah.
it's
Because root 7 is like bigger than 2. Um,
okay. This is an actual inequality question. What is this?
by the way, yeah, I'm surprised. Yeah, by the way, isn't this the quadratic?
Yeah, it's a QM.
Yeah, quadratic mean. This is arithmetic mean, right? What's the theorem? Which way does it go?
QM greater than AM.
QM greater than AM, right? Okay, I think that's
Yeah,
very important. Because it goes the
but
other way.
it's not for like n+1. So yeah,
Yeah,
I
exactly.
feel like
So
is the way to go though. So let me go into the next slide, and this is my idea. So we suppose A1 equals to like A2 equals through to like A N. Oh, just read dot dot equals AN equals 1. All right, and we like AN plus 1 is like equal to 1 minus G, right? Where G is greater than 0. Or actually greater than equal to, and then we can say that, okay, G has to be 0 from this. Yeah. We can do this, right? I'm in the next slide.
Yep,
If you know.
sure.
Yeah. So we can assume this, and then we're like, okay, let's see what happens. So if we expand this, A1 squared plus A2 squared, wait, A1 plus A2 all plus AN over N is greater than equal to square root of A1 squared plus A2 squared plus AN squared plus AN plus 1 squared over N plus 1. And this is like 1. Wait, this is like N plus 1 less than equal to. What's this going to be? It's like that's N as well, so it'll be like 1 less than equal to. Wait. Okay, no. Wait. Okay, I'm just gonna expand this using the thing I was saying before. This is like. Okay, so what's this thing again? Much of N plus 1. So you just remove that bit, get rid of that bit. N plus 1. So is going to what m plus 1. Hmm. This looks like you can probably rearrange this to something. I swear there's an identity for this. What is it? Let me think. This is like 2. Squared. Okay, yeah, it's like boring. What's the identity? I swear, like, what's this do? Okay, so you have this thing, and that would I have messed that up.
We have this interesting thing. So like,
Mhm.
if you just write it out, we have this chain of inequalities, right?
Yeah.
So basically, the quadratic mean has to strictly decrease. Or, I mean, not strictly decrease. It has to, yeah, it has to not increase.
I mean, it'll be strictly decreased if it's not all equal, right?
Yeah.
I swear I've seen an identity involving this before, though. What was the identity? A1. Oh, is this it? This is what A1 plus A2 on 2 squared. Can we write it out properly? What would it be like? I think it's this. This is just what I squared over n. Oops. This is what I swear this is an identity. I've used this one before. What is this gonna be? N. Yeah, this will be this, right? Yeah, that's right. Tony,
Yeah?
have a look.
Yeah, I'm looking.
This looks right, yeah?
Like what does?
This thing. I'm trying to prove this expression.
Is this supposed to be an operator here? Wait.
What?
Oh, is this?
It becomes this. This is just this line. And this becomes that.
Oh, you're trying to prove the top expression.
Yeah.
Oh, I
Trying to
see.
prove that.
Oh, I see.
This is like less than that.
Wait,
This
why,
looks right.
why? Is it?
Well, just look at my steps, right? And
I am.
each one, this square thing has all the two terms, right? A1
Yeah.
through to AN, and like there'll be n minus one a squared terms, and you can just basically or split them up into this. You can put it to this, right? I remember doing this for like some non-standard inequality thing a while ago.
Okay, sure. I mean, yeah, we can.
I mean, this
Yeah,
equals
wait,
to
but
what?
okay, hang on. Why is um, wouldn't you have like one
There's
minus n of every of
there's a negative
most
sign.
things? Oh wait, no.
It's like this, right?
Yes.
Oh, sorry, plus that. And it's like minus. That's minus 2a1, a2, a3.
Why is it minus?
Because I've negated the whole fraction. I put a minus sign out.
Oh, I see.
Yeah. And then this becomes like equal to like minus fraction a1 minus a2 squared plus a1 minus a3 squared n squared plus a2 minus a3 plus a minus 1 minus an. There. That makes sense, right? Basically, this is the proof of QMAM. This is how you prove it.
Oh, okay.
Using sum of squares.
Sure. Okay then.
Okay, so you can use this because it applies in this expression. This becomes sum AI squared. Oh no, sum AI over n squared minus sum AI minus AJ squared. Oh, I less than equal to J less no I less than J less than equal to N over N. And that's greater than equal to AN plus 1 squared. Okay, let me just write this out in a new place. So this is what it's going to be. It's you have I squared n over n. We square the whole thing. And minus, this is going to be sum 1 less than equal to I less than j less than equal to n. AI minus aj squared over n is going to an minus 1, n plus 1 squared. What now? I'm double dipping and using n twice. This should totally be k here. Or something. Because now I can actually use n unrestrictedly. There we go. Okay. Do I really want to bash this equation out and see where it goes? I feel like we need to bash though. It's like the only way, right?
I don't know. There might be some like um, general method involving like. I mean, right now I'm trying to find if there's anything interesting between the difference of consecutive quadratic means,
Yeah.
and also like the the AMs and the QMs kind of like go between each other, right? So like, um,
Do you know any stronger forms of QMAM by any chance?
no.
I don't either.
Why would you ask me? I know nothing about inequalities.
Like you know, like the stronger form for A and QM is like A minus B squared over 8A and 8B.
A what?
It's like what is it? If A greater than B,
Yeah.
then it's like AM minus GM is like between A minus B squared on 8A, wait, 8B, and it's like A minus B squared on 8A. That's a stronger form of AMGM.
What? Okay, interesting.
It's something like that, I remember. It's like not difficult to prove at all. It's just like you expand it, it
Yeah,
works.
yeah. Yeah, no, I don't know anything like that.
Stronger form. Okay, I'm probably not gonna try and expand this out anymore just because it might not be the right way. Um, let me think. What else can I do? Okay, so we know the AMs and the QMs must converge to like some limit, right?
Is that true?
Well, they have to, otherwise, like the they either converge to like some limit greater than 0, or else the problem's wrong.
Wait, but what if they just like kind of? Oh, right, because they have to keep decreasing. Yeah.
It's a decreasing thing that has
That's
to
like
convert.
Bolzano-Weierstrass or something, right?
Yes, but I can assume that's true. If it's decreasing and is bounded
Yeah,
from
exactly. Bound from below, then it converges somewhere. Oh no, that's not Bolzano-Weierstrass. That's something else. But it's like, yeah, it's easy to prove. Anyway,
mobster, isn't it mobster?
what mobster? What?
Monotone bounded sequence theorem.
Oh, okay, that's not what we call it, but okay, sure.
What do you call it?
What do we call it? I don't think we have a name for it. We just call it. We just know it by like
MPSC.
yeah. Like if it increases and is bounded above, then it converges somewhere.
Yeah. Yes, we are putting analysis into this now.
Yeah.
Okay, I need to think. Okay, let me give these things some fresh names. So let AN. No, A. I can't use AN. That's the worst.
Nice.
Okay, what's a mu? Mu is used for mean, right?
Sure. Yes.
Mu n equals to A1 plus A2 plus dot 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 plus AN over n. And what can I use for QM? Just QN, I guess.
I was just using AM and QM and just put the
Yeah,
subset there.
but this has one too many letters, so I'm just gonna.
Sure.
be like this 1 squared plus 2 squared. Okay, the limit can be 0 though, right? Because it
Yeah.
could be just even just decreasing forever.
Yeah.
Hmm. So now we have un squared minus qn plus 1 squared equals to like is like no wait. Let me read this. Okay. Yeah, what do I know about this sum of squares over mean of some squares? Well, only mean just sum of squares over n. This is like this is the sum of all your possible displacements.
Yeah. If I was doing this contest, I probably wouldn't be able to solve this problem. So you're gonna have to carry us.
Yeah, I just have to think of it because it's an inequality. I'm just trying to think what's something nice you can do. I want to use mu n again, so maybe like, but I don't want to use on this. I want to find some expressions like gradient of 2. Okay, Tony, come here. I just want some of your creativity because you're a combi genius. Slide
Where are
11.
you? Where are you? Okay, 11.
Okay, so can you tell me something simple that the right-hand side of this inequality here is greater than or equal to?
Um,
Something that's like not simpler than this expression.
so hang on. This is like this expression. Oh wait, what is this expression? Um,
Because currently it's like not that simple of an expression. Can you just think of something simpler? I just need ideas, that's all. I'm not sure what's happening, but A1 is greater than or equal to AN, right? Because it's decreasing.
oh, do we know that? Oh, okay then. That's nice.
Not increasing, right? If it was increasing, then the band just stops working,
All
right?
right. Um,
You can prove it very easily.
so yeah, like each of these squares would be like subtraction. You like subtract the row from the column, and then you like square everything.
Mm-hmm.
And then you like sum everything. I don't know. Like this is very weird.
I just need you for creativity, that's all.
I have no idea. So each of these would expand to
Yeah, I have an idea.
a1 and ai minus two.
What if I like this is like grading to like some
A.
subset of it, right? So if it's like 1 over n, since we can keep most of them constant except for 1, we can assume it's like something like this then, right? I Okay, yeah, so here's my idea. So in there, like your equality occurs when like all of them are equal, okay? So we suppose that most of them are equal, but not all. It's like this is grading to like ai minus ak squared, yeah, where k is something fixed.
Yes. Okay.
Yeah, so you see how that? I think this might be nice
I mean, that's
because
just
basically
because
this is a
you're removing a bunch of squares, right? So
yes,
obviously this is going
basically
to be
because I'm just gonna
yeah.
say that at the equality case they should evaluate to 0, right?
Yeah, yeah.
Yeah. So that's why I'm thinking like, okay, if I get rid of them, then this might be nicer because this still has enough complexity that you can do stuff with it. But now I don't have to worry about so many terms and choose 2 terms. Okay, what is this equal? This is like uh so it's like ai squared. This is gonna be ak squared. Um, minus 2ai ak, which is going to be mu n ak plus and some of this squared over that. So it's going to be qn squared.
So you know in this expression, does ai squared appear in minus one terms?
Yes,
Okay, okay.
because it's 1 less than equal I less than j less than equal n.
Yeah, yeah, okay.
Wait, mu n squared minus. Let's see what does this become. So minus 2 mu plus mu n ak minus ak squared minus q squared equals to what? There's like 2 mu n squared minus qn squared minus mu n minus ak squared. Oh, let's re-square that. Yeah, so this is what we get from that. Is this of any help to us? Wait, maybe the limit stuff helps. Because it's convergent to a limit. So if you have like AK isn't like your limit, then what do we get? Then since mu n and qn are both the approach, okay, if n tends to infinity, right? Then
Yeah.
the right hand side, it goes to like what is it? 2l squared, l squared. It's like l squared minus l minus ak squared. This is bad, right? If an plus 1 squared tends to that. So it's like, what is this? It's gonna be like okay, if AK is like L minus delta. Delta. No, I'm using delta. Should
Surely
be epsilon.
epsilon. Yeah.
Yeah. It's epsilon delta. The AN should be delta. Yeah, so this is like epsilon implies like L squared minus epsilon squared. AN plus 1 squared. That
Right.
means like AN plus 1 is like, oh, is like, let's think of L minus epsilon. A less than, sorry, not less than, it'd be like less. Yeah, for some epsilon greater than 0.
Right. Yep.
Yeah.
Wait.
Then like,
Then that squared equals that squared. Oh yeah.
but that would make bn. That would make your your thing, your mu n, right? Because mu n must converge, right?
Okay.
So that means that mu n must, and mu n is strictly is like decreasing. It's not increasing.
Yep.
If one times L minus epsilon, and it converges to L, that's bad, right?
Oh. Wait. What?
Okay.
So we're
So
saying L is the limit, right?
yeah, L is the limit
Of what?
of both mu n and qn.
Okay. Yep. Okay.
Because we have this thing, right? Mu n, qn greater than u, mu n greater than qn plus 1.
Yeah.
Yeah, so they must be convergent to something.
Yes. Yeah.
Yeah, so that this, so now we have that like if a k for some index k isn't the limit, then that means that an plus 1 is l minus is less than l minus epsilon.
Wait. Say that again.
If ak
Yeah.
is is not at the limit, right? If ak
Yes.
doesn't value
Yes.
to the limit, so it's got value like say less than the limit,
Okay.
then an plus 1 is going to be L minus epsilon. Well, it isn't going to be, this could be like either L plus minus epsilon, because that doesn't change the sign there.
Right.
Yeah. It means that an plus 1 is less than the limit. But since A is a decreasing sequence, that means that like your mu n value will
Will
be
also
less than L
decrease.
minus epsilon. the limit for that will be less than L.
Right, right. Wait, so you're saying that if AK at any point goes below L,
Either below or above. It doesn't matter. Because the thing is, the right hand side, this thing is going to be less than or equal to L squared minus epsilon squared.
oh,
Yeah. Because you can have L minus AK being epsilon or minus epsilon. Both are the same.
oh, minus this. Oh, right, right, right. Yes, yes.
Yeah.
And that implies that. Oh, right. So even if it's above, then the next term is below.
Yeah.
When you say right hand side here, what's that?
Right hand side of this.
Of what? Oh, oh,
That thing.
oh.
This works, right?
That tends to. Yep, L squared minus L minus. All right.
Wait, it shouldn't be epsilon. It should be like delta. But like. Because like that's not going to be epsilon strictly. Same epsilon. So yeah. It'll be L minus epsilon delta. What is this analysis?
Isn't it? Isn't it epsilon? Wait, what? If this is list. Oh, oh. Right.
This makes sense.
Yes, but if that's delta, and not epsilon, then doesn't that mean?
Well, delta is greater than 0. And that's the thing. An plus 1 is therefore strictly less than the limit.
Yeah, but I can't like.
And
But I can't still converge to the limit, right?
Huh? No, because it's decreasing, right?
Wait, when did we prove it was decreasing?
The sequence has to be decreasing, right?
Oh, because the average is decreasing.
Yeah.
Right. Oh, yeah. Fair enough. Oh,
Yeah. I believe
yeah,
they start like, yeah, it can't increase at all.
right. Wait, so does that mean the average has to eventually go less than L?
L. If this is the case, if it is never at the
Right.
limit, then it has to be less than the limit.
Oh, right. Yeah,
And
true.
that would contradict that it's a limit.
So okay, wait. Does that wait? What does that finish the problem or what?
You think so?
Why is this analysis?
Yeah.
Nice. All right. So
You want to double check?
yeah, let's double check this. So where do we start?
Okay, firstly, let's prove that the sequence is actually decreasing because we haven't actually formally proven it.
Right. I think that's actually known.
Huh?
It's like well known. If the like moving average decreases.
I'm fairly sure one of my inequalities just proves it.
Yeah, sure. Yeah. Oh wait.
Well, yeah, okay. If the arithmetic mean of the first n terms is less than equal to is greater than equal to the arithmetic mean of the first n plus 1 terms, then it just follows from there.
Doesn't that just mean that?
Okay, look here.
That just means that the an plus 1 has to be less than the mean of the first n terms, right?
I have to refresh my Jamboard. It's
Yeah.
a bit laggy. Okay, so look in slide 12 real quick.
Wait. Sure. Okay. Doesn't that just mean that the an plus 1 has to be less than the mean of the first n terms?
Wait, let me think. Does it? Oh yeah, it does.
Yeah. It doesn't necessarily have to be decreasing.
But that means okay. So if that's let's think of the mean. But like if the first term is like, but it's for every n, right? So the a. Wait. Oh, I see what you mean. Hmm. Hmm. Let me think. Okay, maybe that's not. This isn't a complete proof at the moment.
Yeah.
Okay, but I'm fairly sure this is still useful because I haven't actually used the decreasing pi anywhere apart from at the end.
Right.
So maybe you can salvage this. Um,
But like the thing is, since the mean tends to L, doesn't that mean that like some terms have to be? Oh, wait, does it?
no, all terms could still be greater than equal to L, right?
Yeah.
You just get arbitrarily close to it. Like for example, you could just go like 2, 1, a half, a quarter, etc., and the mean tends to 0, right?
Yes. Yes.
Yeah, and then all terms are strictly greater.
Oh, true. Yeah.
Oh, true. Yeah.
Okay, so what we have is that for large enough n, the limit is the an plus 1, large enough n is going to be less than L minus delta. And for some positive delta.
Yes. Wait, do
Okay.
we have that?
Well, that's what this says, right? For all, this is for any n.
But didn't we assume that
Any
it
n large enough.
decreases?
Huh?
Didn't we
No, we
assume?
didn't.
Oh. Wait, we
Not
did?
until the end.
Oh.
Not until the end. That's why it's like that's what I'm saying. It's probably salvageable
But
because you only
then,
assume that at the end.
But then doesn't that mean that some terms have to be less than the mean? Less than
Yeah.
the convergence of
So
the mean. That's what I was
minus
saying
delta.
before, right? I was saying that is it necessarily true that the sequence has to go less than L at some point?
Well, in this case, it does.
But what about the 1/2 quarter sequence?
Well, that's always above its mean, but this one doesn't. That's what I'm saying. What we've proven is if the sequence ever is not equal to its limit, right? Then there exists a term. Then there exists n. Wait, okay. Let me write it out in a new slide. This is what I've proven. If there exists k that a k not equal to L, then there exists n what's that? Oh. This is what I've proven. Look in slide 13.
Yeah, I was always looking in slide 13.
Yep.
Have we really proven that? What?
That's what this thing is, right?
But then what about the sequence 1/2 quarter?
That doesn't satisfy this, right? This is what I've proven. This is legit what I've proven.
What
If
are
there
you
exists
talking
k,
about now? Just slide 13. Like, wait. Slide 11, okay.
in slide 11, that's what I've proven, right?
You've proven that. So what does the halving sequence not satisfy?
The halving sequence probably doesn't satisfy like this thing, right? The qn greater than mu n greater than qn plus 1.
Oh. Oh, I see what you mean.
Yeah.
But did we use the... Oh, we did use QM in there somewhere. Oh,
Yeah.
I see. Yeah.
That's how I derived this.
Yeah. So you're saying that if this is true, then there has to be terms.
Yeah.
less than the mean. Okay.
Yeah. This wasn't a general analysis thing. This wasn't a general proof that like all sequences satisfy this.
Okay. Right. I
It's
see.
really strong. Yeah, so this is what I've proven.
I
And
see.
that means that for like n large enough, the mean has to be less than the limit, right?
It has to like at least like the mean is now tends to at least L minus delta, right?
Mu mu n like is less than L, right? You just choose like you just choose n large enough, and imagine eventually the deltas will be summed to be something greater than like the other stuff, right? Actually,
No,
wait,
eventually the average has to like it has to tend towards L minus delta or something less than that.
yeah. Wait, what if like the deltas like decrease in value as like you go up?
Oh, I thought you meant delta was for all n. If it's not, then it doesn't work.
No, there exists delta. So it's that for all
So
n there exists delta greater than zero, such that
okay.
that's what I've proven.
In that case, isn't it? You don't even really need the delta, right? Isn't it just a n less than L?
Yeah. Okay.
Yeah, exactly.
And
So that means that okay. So that doesn't
quite strong enough.
but we now do know that at some point the sequence will
Wait.
always be below L.
No. We do know delta is actually fixed. Sorry, delta is
Oh,
fixed
is it?
because
So
it's like
why?
L squared minus epsilon squared, where AK is L plus minus epsilon,
AK. Is this slide
right?
11? Yes.
Yeah. AK equals L plus minus epsilon.
Yes.
The AM plus 1 squared is less than equal to L squared minus epsilon squared. Now, epsilon must be fixed, right? It's a fixed real number because AK is fixed. Yeah?
Say that again.
Okay. So, AK equals L plus minus epsilon.
Yeah.
Okay? So the AK not equal to L, so it's equal plus minus epsilon for some epsilon greater than 0.
Yeah.
Okay? Which means that AM plus 1 squared is less than equal to L squared minus epsilon squared.
Okay.
The AM plus 1 is less than equal to L minus delta for some delta greater than 0.
Yeah, sure. Okay, but that's
And
just
this is
for
true
that
for all
specific.
n, and delta is fixed.
Wait, why is delta fixed?
Because n could be anything in the an squared less than equal to L squared minus epsilon squared, right?
N could be what?
Okay, for n large enough,
Yeah.
this is always true. An squared is less than equal to L squared minus epsilon squared.
Okay.
Yeah,
Or at least it's
it's
it
always true.
tends to being true, doesn't it? Like it.
Well, for n large enough, this has to be true, right?
Um. But like, the arithmetic mean is never actually like it could be never actually equal to L. So it's just like an approximation, right?
Uh, um. Okay, but it's the limit, so therefore that means like eventually it's close enough that like this has to be true, right?
Um.
Eventually,
it
the
is.
epsilon is small enough such that epsilon will be like. Eventually, the limit will be so close that like your epsilon will just over exceed, right? The differences between your limits, right? That's what the limit does.
No, but
Okay,
that,
analysis.
you're saying that epsilon depends on.
Let me just write this out again.
All
Okay, so
right.
go to 13. N plus
Yeah.
1 squared less than equal to 2 mu n squared minus qn squared minus, what is it, mu n minus ak squared? Okay, so this is what we have, right?
Yep.
Okay, so by definition of a limit, okay, so if we suppose that like ak is such that it equals to is not equal to L, right? So like absolute value AK minus L
Mm-hmm.
equals to epsilon.
Yep.
Then epsilon greater than 0. Okay. Then for there exists n such that for all n greater than n, mu n minus L is going to be like less than 10 to the 100 epsilon over that, right?
Okay, sure. Yes.
Yeah. Basically, you can make it so that like the difference between mu and the limit's like really tiny.
Yeah,
And
but
same
then
thing.
epsilon also depends on k. So like you can make like
No, but the point is there still exists n such that this is true because that's what the limit does, right?
um no, because epsilon isn't fixed. Epsilon always also varies.
But ak is a fixed value. Ak you just chosen.
Yes, but we can only do ak. Can't we only like relate ak to like mu k and stuff?
Ak no what? AK is like one of the starting terms basically, right?
Ak is one of the starting terms.
Well, okay. Let me see if I can explain this well. Okay, I hate analysis for this reason. It's very difficult.
Yeah.
Okay, so we suppose AK is AK minus L is like epsilon greater than 0, right? We've
Yes.
assumed that. Now, working within this, then there exists n such that for all n greater than n, mu n minus L is less than epsilon over 10 to the 100.
Okay.
That exists, right?
Yeah. Okay, I see.
So now, does that means that like this equation this way this vacuum cleaner here.
Oh, sure. Sorry.
But do you see what I'm trying to do?
Yes, but I don't see like what like so. Even once you get the conclusion, right? You have ak and you have some like mu n, where n is like n might be like way greater than k. And I don't see how you can relate those two necessarily. Because aren't we trying to get like k equals n or something?
No. I swear. Okay. Is this still a vacuum cleaner in my background?
Kind of, but it's not that bad.
It's not that bad. Okay.
Mm-hmm.
I'm gonna put your volume up. Okay. Anyway, so mu n there exists n such that this is true.
Yeah.
And basically, my point is that like you can say that basically that there exists n such that eventually this epsilon term you get here, epsilon squared term here, will just be much bigger than any L minus like delta term over here.
Wait, is this? Wait, hang on. Let me use yellow. This is supposed to be n or k?
K.
Oh, what?
AK not equal to L.
Yeah, I know,
That's
I know.
I know.
But
Where do you
like,
think I'm
how does that have anything to do with a n plus one?
Oh, you want to see the derivation?
Yeah, sure. Is it on page
AI
11?
Yeah. So you remember the AI minus AK stuff?
Oh, you just picked an AK.
Yeah.
Oh, that's what you're doing. Oh, I see.
Yeah.
Right.
Right.
All right.
Okay, sure. Yeah, yeah. That's yeah. I can see how it comes.
I can see how it comes.
So basically, eventually this epsilon square will be bigger than like wherever delta term there'll be here.
Yeah. Okay.
L squared. So therefore, this will be like eventually, therefore, am plus 1 squared is less than or equal to like L squared minus like some, I don't know, delta, where delta is strictly greater than 0.
Mm-hmm.
And it's like and for all n,
Yeah.
and so it's fixed, yeah. And therefore like am plus 1 like less than like L minus what do you choose after delta? This delta. Let's go. 0 for all n. Okay, so that's what we have. There exists a fixed delta such that am plus 1 is strictly less than that,
Which delta?
which where delta is dependent on the value of epsilon.
Okay. Mm-hmm.
Yeah, it's like you can approximate it and stuff, but like it exists,
Right.
which means that the mean must eventually go to L minus delta, right? And it's a contradiction.
Okay. Interesting. Um. Let me read this derivation on page 11. Why is this line true? Wait, are you on page 11?
Page what?
Why is this
What?
true?
Because it's equal.
But you have. Wait, where did the 1 over n go?
It became absorbed with the mu n and the qn.
Oh. How about. Um.
And like there's NAK terms, so like therefore it's gonna be in
There's n minus 1 terms, right?
n n AK minus AK squared 0 for like
Oh,
it's
I see.
I see.
2. Oh. Interesting. So this becomes. Yep, okay, and this one. Qn squared. Where'd you get Qn squared from?
from the sum. It's the sum of AI squared, right? In there?
Oh, alright, this comes here and this goes here. Yeah, okay.
Yeah.
Okay, cool. And then next line, I guess. So that means this. Okay, you just move this onto the other side. Yeah. Oh, interesting. So this goes here, plus, minus, minus, good, okay. And then we get minus this, so minus. Mu n squared. How? Oh, right, because you added 2 mu squared here. A here. Oh, no, that's Q. Interesting. this thing tends to. Huh.
Okay.
That
Thoughts?
is very interesting.
It seems for me.
Sorry.
It seems right at any rate. I hope I didn't
Yeah.
take
I'm reading through it. My only concern is like the whole analysis thing is like
hand wavy because you haven't actually
yeah,
proven it
exactly.
rigorous.
Yeah.
Yeah.
So but yeah. So as long as you do like the like for all there exists stuff. Um,
I mean, that's just the nature with limits. Is like you have to have that there exists like the eventually the difference of the two mu n squared minus q n squared is just gonna be really close to L squared, just because it has to. Otherwise, it won't be a limit.
yeah.
And you just have to kind of maybe formalize that tiny bit more.
So it gets arbitrarily close to L. So
Yeah,
it tends
both
to
of them get arbitrarily close to
go.
L squared, or that expression has to get arbitrarily close to L squared. But like this mu n minus ak term is going to be strictly epsilon squared regardless of what n is, or epsilon squared plus some small delta again,
Yeah.
which epsilon will eventually dominate if you just choose like delta to be like
Yeah.
super tiny, like epsilon over 10 to the 100. Let's see classic Google.
So basically, like different choices of k give you different choices of delta. I mean, different values of delta.
Of epsilon, you mean? Your
I mean,
delta.
like eventually, like so epsilon initially, but then like delta eventually, right?
Oh yeah. Which delta are you talking about?
The one on page 11.
Yes, different values of epsilon give you different values of delta. Yes,
Yeah.
but the point is delta epsilon is greater than zero, so delta greater than zero.
But like L strictly tends towards. I mean, A mu n strictly tends towards L. So we can pick like we can fix k, and then like delta is kind of fixed as well.
Yeah, basically we fix k, and then like n can vary, right?
Yeah.
Large enough, it'll be always large enough. So therefore, you can vary it over all those values.
Right. Yeah. Okay. And then hang on, I'm gonna put this slide over here. Um. Nice. And then.
Oh, yeah.
Okay. Cool. Well, I think that's pretty much solved. You probably just have to do some like formal stuff with the
Yeah.
analysis.
Analysis.
Yeah.
Goddamn analysis.
Should we write up the solutions then?
I guess so. I think we're done, right?
I think so.
Wow, that was much easier than last time.
Yeah. I mean, that can be. Nobody fully solved that combi, but like quite a few people fully solved day 2, I think so.
Yeah. I feel like this last question is probably like maybe hard Q2.
Something like that, but it's got analysis in it, which I mean,
That's why I'm saying hard Q2.
so it shouldn't really even be in like IMO kind of style thing.
Yeah, there's usually no
Yeah,
analysis in there, but like you should know your analysis.
true. But I mean, yeah.
They get
I guess
handed.
you can do this without analysis, obviously. But like,
Well, I mean, the analysis we did is like very like basic, right?
true.
We haven't
Yeah,
used
yeah.
any like
Exactly. Yeah,
I don't
yeah.
know like mean value or something like that.
And you can like prove a lot of like bounded above and increasing implies convergent. I mean, you'd have to like define
Yeah.
what convergent means if
Okay,
you don't know
proving
analysis.
modular isn't that easy, if I remember correctly. It's like you need to do some.
You need to do some supremum stuff.
Yeah. But I think most people can assume it to be true.
Yeah, yeah. Oh well. I mean, um, let's go
Okay,
to
let's go. Up.
yeah. Let's go to type up. Hang on, I get a cup of water. Okay. So let's see. Do you want to write a problem 5 or 6? Or 7 or 8? I don't know. I mean, should we decide who writes of what?
I think you would want your solution from 6, right?
Okay, yeah.
Because
Right,
my
yeah, yeah,
solution,
yeah, 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 yeah. Sure, sure. So I'll do problem 6. I'll start with problem 6.
and I'll do like 7 and 8 then probably.
Okay.
Oh, great! I have to do another tick diagram for 7.
Nah, I won't. I won't put a diagram for 6. I can explain what I mean.
Wait, not gonna lie, question 5, 6, 7. Question 5 was like easy, like D4 or D3, right?
Yeah, yeah, yeah. And
Problem 5, 6, and 7 are like probably day 1. Like sorry, Q1.
yeah. I think problem 7 was definitely harder because problem 6 is like you just symmetry and it dies, and I just
I don't think I would have gotten your solution. I'm just saying. So.
I mean, I don't know. Maybe. I personally obviously found problem 6 easier than problem 7, but
I found problem 7 easier.
okay then. Well, you know.
They're both Q1 probably. Q1 combi. And then problem 8's like Q2.
I don't know. I felt like problem 7 was more like D7 or maybe even D8, but I don't know. That's just me.
I thought it was D6 or D7.
Okay.
I don't know. Maybe it's just because I enjoy those type of combi problems, which is like coloring.
Yeah.
And it was very algebraic as well. My solution for it.
Yeah, yeah. Also, there's like inequalities involved, so maybe that's your thing, right?
Wow, there's 2 inequalities.
Yeah, yeah.
Yeah, but this day was definitely like easier. It was like 20 times easier. Yeah. Yeah.
Oh, whoops! I just realized people can't hear me. I forgot to turn my mic back on.
Nice. How long have you been off?
Oh, like just a minute.
Oh, okay.
Yeah, I was just muting myself so
Pie
I could.
stream.
Sorry.
Pie stream. I thought for a
Oh,
second.
right. Yeah, no. It was just because I wanted to talk to my mom.
I'm draw another N by N square thing. How do I? Okay, here we go. Making another ticks diagram.
Nice. You know about like grid and stuff, right?
Huh?
You know about grid and stuff like tick grids.
Not particularly.
Oh, okay.
I was just gonna copy paste a bunch and then like.
No, don't do that. Don't do that. Okay. Hey, let me. Um. So how big do you want it to be?
5 by 5.
5 by 5.
But I still need to fill in like the bottom squares. How am I gonna do that?
So for that, you what you can do is, um, You can do a for. There's actually this thing for each and then you have coordinates like 1, 1, 2, 2, I guess. And then you do. Oh, hang on, what happened there? Draw. Fill black and then. So now you need to do. I think this should work. Oh, hang on. This is wrong, obviously. It needs to just be this. Okay, let me test this first.
But it should just do them diagonal.
Why did that do a diagonal? What?
Because you only have 1, 1, and 2, 2, right?
Okay, let me
And-
try. Let me.
Wait, why is it drawn? They're not. Is this?
Why does this not work? Wait, why is this not compiling anymore?
Oh, maybe.
Oh, I see. Oh wait, no, I don't see anymore. Sorry, what?
Okay, maybe this will work now. I think this is my line.
Nope, I don't think so. It's still not working for me. Maybe delete this. Why is this not working?
Delete. Okay, it's back.
Yes, it is. Oh, maybe that's why. Let me search up a Tix tutorial again. Okay, I think I know how to do it. I just searched it up.
I have another way of doing it. Now, how do you do range?
What range do you want to do?
1 and 5 minus n.
1 and 1, 5 minus n. That should
Okay.
work. Sorry, let me just do that for now. Okay.
Okay.
Okay, my thing works.
Oh. I was gonna do just this thing, isn't it?
So now you can do like...
Okay, but my thing works, but my thing already works now for us.
Wait, but what are you planning to... How are you planning to do the colors?
Wait. What's happened here? 0, 0, 0. Giving up on this project. What's happened here?
No. I don't think that's a good idea because, if you do that, yeah,
What's wrong with this?
because that means that, you only get like rows or columns of black and white squares. You can't get like individual squares to be black or white.
What do you mean? Just it goes 0, 0, 0, 1, 1, 1, 1, 0, and then she
Oh
goes
wait,
0.
are you trying to like build like the triangle?
Yeah.
Oh, and that's the only diagram. You don't need any other like weird diagrams.
Yeah.
Oh, okay. Let me think then.
Surely this should just work. Why is this being mean?
So from black. So why does this not work? Oh, it's because you can't do arithmetic inside the, so you have to do nm 2 plus plus
Oh.
0.
Jeez.
Okay, this will work. And if you just do this.
Just...
Yeah, there we go. That works. Although, wait, what? Illegal unit of measure. Where's the unit of measure? Oh, right. You can't do arithmetic here either. That's a little... That's very sad.
I need your arithmetic. What the hell? Can I declare a new variable and just be like, okay, this is equal to 3 minus n somehow?
me think.
So I can just
No, that doesn't. Yeah, no, that doesn't work. Tix doesn't have good like.
isn't Tix built off like LaTeX?
It is, but
It is.
you can't do that in LaTeX either.
But then,
Yeah, actually doing arithmetic in tech is a real pain. I think it might be easier to just do.
okay, you can use the Tix library calc for it. I think.
Yeah, you can, but like it's still like. Um, if you just insert all of the, like yeah. There we go.
I just think we've got the Tix library.
Hmm?
I just got the Tix library calc in. Okay, I can go to the first. Yeah, that's the construction of it anyway. Is it called hockey stick identity?
Sorry.
Called hockey stick identity? Is that what the formal name is?
Yes, hockey stick
Hockey stick
lemma.
lemma.
Huh?
Hockey stick lemma.
Hockey
Okay,
stick lemma.
okay.
Lemma? I thought it was identity.
Hockey stick. Oh, okay. Maybe it is identity.
Yeah.
Okay. Yeah, I mean,
I mean, you can just say that, right?
if you
like,
just say hockey stick, that's probably fine.
BRB. Okay, so flipping the board over the main diagonal won't change the score, right?
No.
No, it wouldn't.
Oh. Would it?
If you flip over the diagonal and you also invert the colors.
Yes, and then no.
Yeah, yeah, good. Because that's what I did.
Okay.
So you're basically just changing the order in which they appear.
Yeah, yeah.
Yeah. It's just what I can use to justify that AI is going to, and the A column, AM will be the maximum, not BM.
Oh yeah, sure, yeah.
I just read Papi's solution and oh my god.
Sorry.
I just read Papi's solution and oh my god. You've been doing too much set theory recently, I think.
I mean,
How much set theory have you done in the last week?
like none. But like, what? Why? What?
So much notation.
I mean, we don't really need. Um, we don't need NS
Finality
notation.
multi-set.
Well, it's multi-set because you can have like repeated numbers, right? And then sets just kind of like not proper anymore.
Yeah.
Yeah, and we don't use the NS notation, but I just wanted to make a distinction between the fact that like that absolute value sign is never going to be used to denote the cardinality of the set.
Okay.
But yeah.
Okay, done. For problem 7.
Nice. I haven't even done problem 5 yet.
Oh, look, over 4. Yeah, get rid
In this case, we do. Man, this case bash is honestly so annoying.
I'm telling you, my thing works better. Wait,
I
did
mean,
you
like,
see what my thing was? Basically, if you have a, you switch the last subtraction, and after that, for every addition, you just make it minus. You just make it minus b. You make it a subtraction, and for every multiplication division, it doesn't matter because the sign's preserved.
I mean, like, this.
It's the same idea as your thing, except I think mine just cuts a bunch of cases.
Maybe. But then, like, still, like, this thing I'm trying to prove now is, like, it's trivial, but, like, I'm afraid if I don't prove it, like, there might be marks deducted or something. So,
Oh, okay, then yeah, you should be fine.
because all we need to do is, like, a plus b, a minus b, and b minus a. Like, obviously, you, like, the absolute value of those three can be made with, like,
Wait, overleaf down.
sorry, what?
No, sorry, what? Friend just messaged saying the overleaf was down. I'm like, I'm on overleaf right now.
Oh, what? Is it? Let me check the stream. No, the overleaf seems fine.
Yeah, it seems fine. No, it's okay. Problem 8. Okay, problem 8. Doing this up is going to be a bit of a pain. the hell happened here? Wait, scroll down to what my LaTeX. Just look what happened.
Your LaTeX? Where?
Yeah, the late. Look what happened.
Oh, that's because
Big. I should use big, not left.
yeah, that's because of your fraction thing.
Yeah, that is so horrid. Look at that. Okay, I'm gonna screw that. I'm just gonna go like.
You can just do
some-
like you make the sum not display style.
Make it smaller. Yeah, make it small enough. My overly bugged out. Like a bunch of tweezers. I'll take that. There should be n.
I finally finished writing up problem 5.
Why are color links in red?
Why a what?
Color in red.
Oh, right. We can change that.
Yeah, because it is like an equation reference. It's like red. What?
I mean, you can click on it because it's a link, right?
Yeah. Why is it red? Why not like
Blue?
just make it black? Because it's an equation reference I'm using.
Oh, right. I can just not define the color and it will just be black.
Yeah. I prefer that.
Oh, wait. That doesn't work. Let me. Okay. Man, I'm having such a hard time explaining the construction for odd n in problem 6.
Yeah, I'm just using 10 to the 100 in my analysis.
Nice.
okay, this part is a bit icky. I think I have to use triangle and column.
Okay, nice.
Okay, I just need diagram for this real quick. So, okay, good. Diagram helped that a lot.
This is so depressing. There are no like I can't think of any nice constructions. I can think of a lot of bad constructions, but like they always use like IVT or like some perturbation like argument. I'm just gonna write that, I guess. Well, that was a rip. Anyway.
Anyway. Okay, so the x 10 to the 100 value actually matters. So it shouldn't be 10 to the 100. It's a specific value such that this inequality.
Wait, actually?
Yes, I just did the working out. It's like 10 to the 100 will probably work, but like if if the distance difference between AK and L is like tiny enough,
Okay. Wow.
this is unbounded, so therefore I can choose big X or small X. Well, actually, no, big X. Okay. So as we um, okay, so we choose x equals 4 ln epsilon plus 4. Wait. Can I just say choose x such that x on 4 minus a half minus 1 2x all times epsilon is greater than L, and just say because x on 4 is the left hand side's unbounded, this exists.
Are you asking me?
I don't find a specific value of x for which it works.
What on earth?
Just choose x equals 4. Really fucked out again. Overleaf really needs to work on its
Sorry?
thing. Overleaf needs to work on its software with regards to like multiple people editing because it seems to bug out regularly.
Oh, does it? I mean, it's been fine for me, but I don't know.
As like a line shift. Well, I mean, it's because I'm working below you.
Yeah, exactly, yeah.
Your lines won't shift from my action, so mine will shift from your action.
Unfortunate.
Okay, fine. Okay, writing out the analysis was a bit of a pain, but it's done now. Oh, is the stream still running?
Yep.
We have 13 more minutes or something.
Sorry?
Almost 5 hours now.
Yeah. Wait, how close are you to finishing problem
I
4?
finished.
Oh, you're finished?
Yeah, have a read.
Oh, nice. Wait, I haven't finished problem 6.
God.
Honestly, the construction took me so long. I was trying to think of like a nice way of doing it, but I couldn't think of one, so I went for a really ugly construction.
Wait, you're saying n minus 1 of the angles to 180 minus 360 over n?
That's what it is for a regular Ngon, right?
Oh yeah, oh, for a regular angle. Okay, I thought that was for your construction. Like, what?
No.
That would be bad.
Yeah, exactly.
Okay, let me figure out how to align, but like have it break across a page. Is it allowed page breaks? That gets you to break across a line.
Page breaks.
Yeah. My equation is too long. It might fit. You need multiple pages.
Oh my god, where is your equation? Where is this?
Well, I mean, it's just because it's right on the page boundary. That's why. So there's like a massive
again.
white page here and just right there. Yeah, allowed display breaks. That's it.
Oh.
Yeah.
Wow.
What?
The proof. So much algebra.
Yeah. That was not a nice analysis. I have like 3 variables for like just epsilon delta stuff. Little epsilon, little delta, and big delta.
Oh wow.
Wait, whoa. Daniel posted a nice solution for question 1 in
Sorry?
the. Daniel posted a nice solution for question 1 from the contest, the inter contest.
Oh, the inter-contest? Oh.
Okay.
I thought you were
like,
talking about this.
Nah. I did not know that exists. What the hell is what?
Okay, I think I've finished. Problem 6, finally.
Finally.
Yay, we finished. Okay, but whose solutions are the longest? Your problem 6 has so much writing to it.
I know.
My problem 8's just yucky.
I mean, yeah, my problem 6 would not have as much writing if I used diagrams, but I couldn't be bothered.
It's not that hard to do them on ticks, is it?
No, but like I would never do like geometry diagrams in ticks. You'd always use like GeoGebra, like import, right?
Yeah, true.
But I
You
couldn't
could
be
have done
bothered doing
that.
I don't know. That also takes. They always come out really badly, and you have to like tweak a lot of things to make it look good.
Make it look.
Change the thicknesses and all. It's not that bad. Anyways, read over my proof of question 8 and see if it agrees with you.
Oh my god. Okay. Converge to a limit. L. Oh god. Okay. How does this so on page 9 it says one implies some
Oh, yeah, that
assumption.
thing, yeah, I'm looking at it right now. Okay, so let me see if I've I haven't typoed somewhere because it's possible I might have typoed something. And that might be squares that's supposed to be in the middle. Let me double check. Okay, so n some ai equals 1 minus some ai squared. AI squared, okay, yeah. This is all times by n. Okay, that's right. That substitution is correct. But now I've checked that I've actually subbed this bit into here properly. So that means if you put 1 over n squared here, then this becomes 1 over n squared here, so it's 1 over n. And before there's like a fake solve because I've messed this bit up.
Rip.
Sorry, that's the case. No, this is correct. I'm very sure. I just have messed up somewhere, and my working out's too unclear for me to read it. But I'm very sure this is correct. Should be un squared minus an plus 1 squared should be going like that. That's correct. Now I have to just figure out where this is messed up. Where is it? So multiply this out by n plus 1. Oh, right, okay, sorry about that. There's a slight typo here. That's why. And that's because I was writing fractions. Where am I? This is now it's let me I have to adjust this bit as well. There we go. Have a look now.
Okay.
Basically, I forgot to expand out the n plus 1 part and there.
Oh, right. Yeah, okay.
Yeah. It's just a slight typo.
All right, you added that bracket in. I was just gonna say
Which one?
after unbounded. I was gonna say.
Yeah. Already added it in. I hate analysis.
Hang on a minute.
The absolute value thing follows from like triangle inequality. Basically, A of k is going to be specifically L plus epsilon or L minus epsilon, right? Whereas mu of n is going to be like any value between L and L plus epsilon over.
Sorry, I was talking to my parents.
Okay.
I'm still on the like, then there exists n such that for all n greater than n.
That's what I was talking about.
Okay. This, yep, okay, so.
Okay, so you'll probably want to know where the mu n minus ak greater than 1 and minus 1 over x epsilon comes from, right?
Yep.
Okay, so basically, mu of ak is going to be either L minus epsilon or L plus epsilon, right?
Yes.
By definition, ak is that. And mu n is any value between L and L plus epsilon over x.
Right, yep.
Okay, so then that means that the minimum value mu n minus ak can ever take, that's the value of that, is when mu n is going to be L plus epsilon over x, and ak is going to be L plus epsilon.
L plus.
Just draw up. I did a diagram of it on the Jamboard.
Oh.
Look at page slide 13.
Okay. Yeah.
Yeah, so I've done like a number line kind of thing.
Yep.
Yeah, and there's like L plus epsilon, and there's L minus epsilon. So you can see the biggest distance is when it's like over here. The smallest distance is this thing, right? This is when I was still using epsilon x equals to 10 to the 100, so this should be x. But like, yeah, that's x. But if this is L plus epsilon over x, then there's going to be 1 minus 1 over x. And there's just going to be epsilon. And yeah.
Okay. Yeah. Sure.
Basically, triangle inequality. And then this bit just comes from like positive maximum values, all that kind of stuff.
Wait. What? How did you get to the second line of the next thing?
Huh? What?
How did you get to the second line of the next thing?
Oh, well, mu of n is less than equal to L plus epsilon over x. It's less than that, right?
L plus epsilon over x.
That's
Oh, right,
by
yes.
And q of n is going to be greater than or equal to L because it's decreasing.
Right, yes.
And that thing comes from like your the thing before. Analysis. Basically, lots of triangle.
Right, yep.
Then you expand that out, and you collect new terms.
Okay. All right. Okay.
and that's equal to L squared minus delta, where delta equals that.
Wow.
That and that is also positive, right? And it's greater than 0. Might be tiny, but it's greater than 0.
Yeah.
And then, like, delta equals that, and it follows from the next stuff. That's by
Okay. Wait.
definition of what I did.
So this.
So you basically choose delta as well. So you can make delta really, really big as well. Like, make it x if you want. But, like, don't actually make it x. But, like, you can choose delta to be super big if you want.
So this equals that.
Or you can make it small. It doesn't really matter. The point is it's positive.
Okay. That's the equality comes from. This equals.
Oh, it's just delta.
Wow.
This is so bad as a proof.
Right.
It worked,
Okay.
but I hate it. But it was going to be an analytic anyways, I think, because it's in positive reals
So that
and
equals.
not in, like, integers.
Right.
Just didn't expect it to be this analytic.
Okay. Yeah, I mean, I checked all the algebra, and I think the algebra works.
Yeah. You only read problem 7, just double check that's all right. It should be fine, but
When you say choose AM equals max of those things,
Choose M such that that's the maximum.
yeah. Are you like kind of saying that if a B is maximum, then actually we flip the board over the diagonal, so it becomes a row?
And yeah,
Right. So basically, AM is a row.
yes, yeah.
Okay. Okay. Wait, and the row contains the maximum number of white.
It's the
White.
most monochromatic row, basically.
Sorry.
It's the most monochromatic row.
Right. Right. Yeah. Okay. Okay.
Yeah. This entirely gets rid of like the ordering argument that we can order it.
Hang on. You know how you proved that every square in this column except for the nth one is black?
Yep.
So that means that that column is probably going to be one of the most monochromatic, right?
Yes.
Yeah. So that means that the nth row.
It's either n minus one or n white.
Yeah, it's either, yeah, exactly, right. So if the square at is white, then we have a row which is all white. But if it's black, then we have a column which is all black, which is a contradiction. So it has to be like that. That row has to have all m be white, right?
I think, but I don't feel too comfortable with that argument, so I'm just gonna go with my one.
Sure, yeah, yeah. But basically, like you just repeated
Yeah,
the thing, right?
Yeah, yeah.
Okay.
I get what you're saying, but I feel safer with this argument.
Okay. Cool. Yeah, I think that works.
Yeah. I read through your thing. Sounds reasonable.
My which one? What?
Your six.
Oh, right, right.
Yeah, looks alright.
Yeah, the construction is like longer than the proof that it can't work.
Yeah. My things are just longer,
Yeah,
but it's because my thing had equations and then yours didn't.
yeah, yeah.
Mine had so many equations in Q8.
Yeah. Oh,
Yeah,
man.
yeah, we're done. Nice.
Oh, man. All right, then.
CMC, we've got gold altogether, I guess.
Yeah, yeah.
Not the best in the world, but gold.
Uh,
So we're nearing the end of the stream then.
yeah, okay.
Yeah.
Well, then, yeah, see ya, everyone, I guess. And,
So like and subscribe button.
yeah, exactly. Go to AMQM, the like button,
Like button.
and
And
rearrangement inequalities, the subscribe button, and
yeah.
okay. All right then. Yeah.
Next,
See ya.
Yeah.
like IMO next time, presumably.
Maybe.
Uh,
Yeah, probably.
Yeah, probably.
Next big one
I
is
can't think of
IMO.
any contest in between.
Yeah, yeah. Okay, well, I guess we'll see everyone at the IMO maybe if we live solve it.
Yeah.
Yeah. Alright.